The next speaker is Fedor Bezrukov, actually, reheating and the Higgs-R2 inflation.
Okay, just a second, I'll move this out of my screen. Okay, good. So first, thank you for inviting me to this very interesting workshop. It's really nice to speak on the Quark conference, even in this online form. And I still feel that it is a Quark conference, so yeah is a bit wrong. Okay, and in this talk, I will speak about Higgs-R2 inflation, preheating, and mostly about preheating it. And actually, there was an excellent talk at the very beginning by Alexei Starobinsky, which basically told the whole story. So I will continue and try to add, try to start it from slightly different direction and probably give more technical details of how it all happened. I'm not sure that I will be able to add a lot. Oh, yeah, okay. So my part of introduction goes not from gravity, but from particle physics a bit. So my logic is that what we know about particle physics is that the results of BioHT tells us that it's a perfect theory which describes basically everything. And last but not least, we know now the mass of the Higgs boson, which is a pretty non-trivial discovery, telling us that the Higgs boson is, that the coupling constant of the Higgs boson is small and stays small up to Planck scale, so that we can work with this theory at all scales without worrying too much. Oh, okay, well, at least we can work with it perturbatively within the machinery of our QFT. So, excellent theory. However, we know that we need inflation in the early universe for many reasons, to solve some generic problems like singularity or something, or for more practical reasons to generate primordial perturbations, which are observed and non-trivial dynamic, clearly non-trivial dynamic. And as far as we have a scalar field in our possession, in our particles, it's tempting to use it as an inflaton. Okay, we already have a scalar field for which we actually is there. And if we use the quartic inflaton field, quartic potential for inflation, it's a very nice inflation, more or less. However, it clearly requires to produce observational results extremely small coupling constant lambda, which is not that small. So there we go. So, however, this is not too much of a problem. It was actually solved long time ago. It was suggested by Z, Smolin, Spokojny, Sosolopik, Bond, and Bardeen in old time ago. And it was observed that if, in addition to the quartic potential of the Higgs, there is a non-minimal coupling of the scalar to the curvature, that makes the potential effectively flat at large field values. More about it later. So it solves it very nicely. And the important point, so this idea was revised by Shaposhnikov and me some time ago. And the key observation that why this, probably my own small historical insight, why this idea from old time was a bit forgotten for that many years. The reason is that if we use a probe Higgs in this setup, then we can observe that the vacuum expectation value is basically irrelevant to the whole discussion. Basically, the required value of Xi is so that psi multiplied by the current value of the Higgs field is infinitely smaller than the Planck mass, and we can forget it. Which is pretty different because in the old times, this date when this was previously analyzed, 99, coincide with the understanding of Grand Unified Theories, where the Higgs at that moment, which people thought for inflation was the Higgs of the Grand Unified Theories, where the wave was basically at the Grand Unified scales. And then actually this was not true. So you got basically the Planck mass generated by xi squared equals m Planck, which basically removes the field from the theory, making it completely decoupled from everything else. So in that case, it turned out to be not a very interesting setup. However, for the case of the normal Higgs, seems very nice. So, okay, how it works? Oh, first observation is that working with this theory in the so-called Jordan frame is pretty complicated, just because this term h squared r is actually a kinetic term, so all the equations are hard. So the normal way to deal with it, the simple way, is to change the variables with which you work, which is just a change of variables. You define a new metric by conformal rescaling, and then basically after the smoke clears up, the story boils down to a different potential for the Higgs field, for the scalar, which is exponentially flat at large field values. And the only parameter it depends on is, instead of lambda, it depends on ratio of xi and square root of lambda. So instead of taking small lambda to get the probe amplitude of perturbations, you can take large xi. It works pretty nicely. Your preference of working in Einstein frame and Jordan frame here is pretty technical. However, it's important to remember which frame is crossed if you start adding additional fields to this model, additional matter. So basically all the rest. If you add, say, quarks, if you add QCD, you should be careful in which of the frames you write the simple standard model Lagrangian, which you are used to. So normally it's written in Jordan frame. However, still any analysis is much simpler in Einstein frame. And so kind of it's physically simple. Okay, so basically we have this nice potential. Afterwards, the moment we fix the normalization, all the constants this potential is fixed, the prediction of this potential is given. And actually, after that, we arrive to the fact that the prediction for the tilt and tensor to scalar ratio are somewhere here. So basically, it predicts very small tensor to scalar ratio. And actually, it turns out that cosmological observations actually favor this type of potential. They dislike normal power law potentials because most of them produce too large tensor to scalar ratio. So pretty nice theory. Of course, I have to mention that the R squared inflation gives the prediction somewhere in the same place because the potential is very nice. So it's very hard to distinguish. And we'll arrive to R squared inflation in a moment, turning that it's in some sense even better. Okay, so basically at the moment we kind of use the Higgs field for everything, solve the problem, we're extremely happy. Is this true if we consider quantum corrections to the whole story? Because for the moment, our analysis was three-level background, and all our quantum effects that we were speaking about were generation of perturbations at inflation, which are quantum effects, of course, but these are three-level quantum effects. So they're not too quantum. They're kind of follow from the classical evolution, the lowest order. And the analysis of the model actually shows that yes, if you look at it, it has high order operators suppressed by pretty small, relatively small scale in Planck divided by Xi. So potentially this model is dangerous. It was soon understood that this is not that dangerous. So if you carefully write the background, expand the fields on top of your evolving inflationary background, you are going to have high order operators for perturbations of background, which are suppressed by some scale that changes with time, that basically is different during inflation and today. And actually, if you plot so value of the field versus the energy at which tree-level calculations would fail, we'll see that depending on which tree-level observables you look like, they have problems at Planck divided by Xi today, and much larger scale, which is Planck and Planck divided by square root of Xi during inflation. So at this moment, seems everything is fine. So Hubble scale is inflation is Planck divided by Xi. Energy scale is inflation is Planck divided by square root of Xi, both small by small couplings constant lambda. And the problems at inflation are at best at Planck divided by square root of Xi. So seems no problem in the theory at all. Excellent, excellent theory. However, as we will see in a moment, the moment we'll study reheating here, this will cease to be so. And before we go into reheating, so when we'll start studying reheating, we'll see that this is a problematic thing. So basically, we will be forced to study the theory beyond the region where we can calculate perturbatively in the theory. So we need to invent something to deal with it somehow. So how can we deal with theories which are not tree-level unitary? So the only way that we technically possess at the moment is to UV complete it. Strictly speaking, we don't know. Strictly speaking, it's not required. The theory may enter some more strongly coupled regime and just work by itself. Unfortunately, we just cannot calculate in that regime. So this is a possibility, but we cannot really trust it. And the simplest solution to make the theory UV complete is actually join the theory with the original inflationary model by Starobinsky, the R-squared. So this was suggested some time ago and analyzed in different ways. What's the hint here? Why it works is that because if we look at the theory with added R-squared theory, this theory is complete after n Planck, which you can clearly see if you look at the potential for the inflation in R-squared theory in Einstein frame. This is the exact expression for the potential, and you see that if you expand it, it's actually expanded in the powers of only m Planck. So the only problematic scale here is m Planck. So up to m Planck is good, and then what takes out if you make the constant beta large enough or the mass of the scalar particle that appears from this operator below, so small enough below the problematic scale, then you get a classical perturbative compilation of the problem. Everything works nicely. You can calculate with it without any problem. To make the story complete, I have to mention that one can do different ways, perturbative ways to complete the theory suggested by Judici and Lee in 2011 with adding additional non-minimally coupled scalar, which actually is a slightly more general way of the same construction, because it's mostly using the scalar in the induced gravity regime, which is basically R-squared model. So just written in disguise. There are some attempts to work non-perturbatively. There are works by self-healing by Kalmet, works of local completion by Tokarev and Koshelov. However, as far as I don't know how to calculate within this setups, I will stick to Higgs inflation R squared model. Actually, what is this? Where we arrive here? So if we want to analyze here, we arrived instead of the original Higgs inflationary model, or even more original, so the first one R squared model, we arrived to some combination of these two. We actually arrived to a large class of this model. And the question appears, can we distinguish between them somehow? And actually, as far as also what means the large class of similar models, it means that the potentials in inflationary region in both of these models is basically the same. So inflationary predictions look very similar. So if we want to take further insights here, we need to see in the reheating of this model. Why it's preheating? Because different efficiency of the preheating, which one could expect different, because in this case, you basically get your all energy in the Higgs from the very beginning. Here you have all energy in the gravity sector from the beginning. You would expect this to reheat much harder, much faster than R squared, leading to different scales where different moments of time, different field values where the pivot scales exited the perturbation is generated at inflation, and effectively because of that, slightly different than that. So careful analysis preheating is extremely important here, and the only way to distinguish this or any of its combination. And actually, as I said, yes, so in general, there is a whole family of the models, not just Higgs inflation R squared, because in the combined equation, instead of just beta or just psi squared divided by lambda, the inflationary perturbations are governed by a combination of them. So one can take the plane of beta and psi and get the line which gives to good inflations. And along this line, one can go either to this region, which would look like Higgs, or to this region, which would be R squared. This small part here is where we cannot calculate in Higgs inflation whatsoever, because you get beyond strongly coupled. After all this is weakly coupled. Here mostly Higgs, here mostly R squared. So let's see first let's see how it behaves. I'll repeat it shortly, but then let's see how it behaves. Okay. So one step back. Sorry. So to understand how it behaves. Wrong slide. So this plot was already showed by Mr. Rubinsky. Is in this model, you can also transfer to some Einstein frame, which is a bit complicated because the kinetic mixing between the fields is still complicated. However, you get the potential with two fields, where this is Higgs direction, this is scalar direction, but the potential turns out to be very narrow valley. And if you plot the potential along this narrow valley, the potential is basically again the same as in Higgs or R squared inflation. So basically, effectively one field inflation, everything is easy. So the question is how it works. So what happens next? Okay, so let's return to the ideas of how the reheating works. So the first thing that I have to mention is why actually the Higgs inflation by itself is bad. Bad means impossible to calculate predictions at the moment. It turns out that naively one could guess that at preheating, all the particles have the masses of n Planck divided by psi multiplied by chi, which is not very large, and all is safe, no problem. However, which is the natural formula, so where chi is the Higgs field, and this is basically a naive formula of all particles proportional to Higgs field. This is squared. However, there is a very nice observation made by Emma. that which I'll repeat it because it's just beautiful. If you write the massive vector field with a time-dependent mass, the moment you try to get it to equations of motion for individual components, while you'll move from this action to the equations, you'll need to project out the three different modes, the transverse and longitudinal modes. Transverse modes will be very easy projectors, which will project it immediately. And the projector on the longitudinal mode has lots of time derivatives. And if your MA mass is time dependent, while you project out the longitudinal modes, you'll differentiate many times this MA, and the effective mass that you'll get for the longitudinal modes will be not this quantity, but a crazy combination with lots of derivatives of MA of time. And if you plot this function, you'll see that this function has very narrow and very high peak. How narrow, how high? They're basically M-Planckish high and M-Planckish wide in the time. So you immediately conjecture that this is a very, very fast changing particles with very fast changing mass, expecting production of Planck scale-ish particles, of particles with Planck scale-ish momentum during the evolution. And producing Planck scale particles is something that we definitely don't want. We're definitely beyond the applicability of it. So, what to go from here? As we said, so the solution to go from here is to go to UV complete theory, and this was done by the group of Starobinsky very nicely, and they calculated the motion of on this background, and calculated the mass of the longitudinal modes, okay, or Goldstone boson in that case, but basically longitudinal mode. And this was, instead of this plot with the peaks, the plot was like this. So there was large peak, second large peak, and so on, which happened when the field reflected from this point. However, this peak turned out to be not that large and not that wide in the regularized model. And basically, it was concluded that this peak doesn't produce a lot of particles. So on the first one, we are saved. So no disaster happened. The model is fully regularized. We are very happy. However, the question immediately appears, okay, how this object reheats? And there, our observation appeared by me, Gorbanov, Anya Tokarev, and Chris Shefford. And the observation was the following. So if we look, so this is again the plot of the same potential, just density plot, so Higgs scalar on direction. We arrive from inflation, do something, and reflect back, so oscillating. And depending on the parameters of the model, there are situations when you reflect, so as far as there are two values, to one value, or back into the same value where you arrive. And obviously, looking at these two pictures to the left and right, you could guess that there is a situation in the middle when you reflect between them. Reflecting between them is reflecting up to this point, right? Up to wrong direction, so to this point. And what is this point? If you look at the potential along this line, this potential is actually upside down tachyonic. And as far as you arrive to a place with tachyonic particles, you expect that the particles will be produced copiously and immediately here in this region. And this is really the case. So one can calculate, again, this, okay, one can check that there is a tachyonic mass there. There is really a large tachyonic mass there. Let's skip this point. And one can calculate the production of particles by calculate the Bogoliubov coefficients, calculate the production of the particles in this regime, and really see that, so this is the moment when the mass is tachyonic here. and these are two types of particles, say Higgses and Ws. This is pretty irrelevant. So basically, they are copiously produced if we get into this central regime. So the conclusion, the naive conclusion was that it's immediate reheating. However, there are catches in this conclusion. One catch, okay, actually both catches you can see on this picture. First, so what these three pictures correspond to? These three pictures correspond to different parameters of the model. So different places, different betas or different size, different places on the line between Higgs and Higgs-like and R²-like inflation. And you see that sometimes you reheat actively, sometimes you reheat, so you produce particles much less active. So that's one catch. And another catch is the situation where you produce them in large amount. You can notice that this line actually corresponds to the energy density of produced particles. This is the energy density of the inflaton itself. So you produce more than you have in the background. Okay, so you are mistaken because you are neglecting back reaction of the produced particles to the input. So one should be more careful. So one should take into account back reaction, one problem. And another problem is again that if you can calculate at which value of the parameters beta you get to the stoichiotic regime, and you get only at particular values of beta. So this is for smaller beta, and actually for all range of beta, it was calculated in the work by the Rubinsky group, saying again there are some periods. So for the whole range of betas, there are only particular moments when you get to the stoichiotic regime. So the question is, what happens if you are not here? And the question is actually twofold: either how you reheat if you don't hit stoichiotic regime on the first installation, or you can ask yourself what happens when you return to this zero next time, because you return to the zero many times while oscillating, and you can hit the tachyonic position on the next oscillation. So, however, it's pretty hard to analyze analytically what happens in the next oscillation. So, what was the solution? How to happily calculate both back reaction and both what happens if the field, scalar field oscillates several times? The answer is try to do numerical approach, full numerical approach. Luckily, you don't have to. So if the coupling constant in the theory, if lambda is not that very large, you can analyze basically the occupation numbers, quantum occupation numbers grow quite fast, and you get to the situation where the system is still linear, but the occupation numbers are already large, and you can continue to analyze the system just classically, because the quantum effects basically disappear. Actually, Alexei already told you about this fact. So the idea was realized in the numerical codes, first by Hlebnikov and Tkachov, and then by different people. So you take your system, populate, so take it somewhere after the end inflation, populate the fields with Gaussian perturbations corresponding to the vacuum fluctuations, imitating vacuum fluctuations, and then just solve classical equations of motion and see what happens. Oh, there were some problems in our case. There was a non-canonical kinetic term, so not all codes work. So we used, instead of very efficient codes like lattice easy, we had to use the code Gabe, which can deal with non-canonical kinetic terms. However, strictly speaking, it turned out that this is not too relevant for our case, because all this tachyonic stuff happens when the non-canonical kinetic terms already died off, but it was done. And the most interesting case is that, as always with numerics, one has to arrange the code so that the whole range of interesting modes, that interesting frequencies that evolve non-trivially should fit on your lattice. So, and actually, here it turned out that the requirement that the modes produced pretty far in the tachyonic region don't give you preheating with occupation number of the order 1. It really happens only if this combination is small, which basically limits us to calculating in this region. So basically, we actually cannot calculate in Higgs-like regime. We can calculate it only somewhere in this region of parameters, because if we go in this direction, then the tachyonic produced modes will give you full reheating with occupation number of the order of 1, which is essentially quantum. If you go in this regime, then basically we'll need infinitely large lattice to grasp the whole range of relevant modes for reheating. So it's basically here, it's in principle impossible with semi-classical calculation. In this direction, it's impossible on a realistically sized numerical. Okay, so it was done. And what was the observation? So the outcome was the following. So two outcomes. So first, we observed that tachyonic behavior, if you plot the tachyonic mass, can happen not so all this going up and down corresponds to the scalar fields going up and down. And if you start so that on the first oscillation you don't hit tachyonic behavior, you can hit tachyonic behavior at some, so first oscillation, second, third, fourth, on say fifth oscillation. So you can still get tachyonic behavior. That was first oscillation. Then you generally observe that at late time you produce perturbations, which basically give you thermal masses to all your modes, which turn off the tachyonic behavior at late time. However, for this I don't have a good analytical understanding. Experimentally, for all values of beta that we tried, tachyonic behavior happened first, and only then enough particles were produced to block the tachyonic behavior completely. So basically, the answer is that for any value of the parameters that we could study, the system got into the tachyonic regime. So this was a universal way to reheat numerically. Okay. So this is basically the outcome. So you can see the growing modes. You can see some tachyonic behavior happen. Then there is some growth, which is some more complicated nonlinear resonant dynamics, which is hard to understand analytically in this model. However, it basically boils down. So this orange line is the produced particle. So number of e-folds. So you see that you get it reheated, say 1, half. So you get the model reheated. So that was the answer of full numerical simulations by Shepard and me, saying that it reheats at any moment, and actually it happens pretty fast. What it actually means, so returning to again to our, what it means from the observational point of view, it basically means the following. So we can plot the parameter beta. Here, this point would correspond to, say, pure Higgs inflation. And this point somewhere here corresponds to the pure R² inflation. And then one can calculate the preheating temperature, calculate the number of e-foldings, and okay, here I calculated so this is not a real plot. This is an instantaneous preheating in strong coupling. Okay, basically the fastest possible in principle. This is the perturbative reheating in R², which was calculated before. And these are the points in the region that we managed to calculate. Well, actually, looking at this, you can guess that the fact that we were unable to calculate in the Higgs inflation is not very interesting. Most probably, they are somewhere in between. It's still much more interesting to calculate what happens between this point and this. This is actually not yet done fully. And how then, if you recalculate this number of e-foldings into the observed values of spectral index and R, you will get for pure R squared the point somewhere here. For this regime, you'll get somewhere here. Okay, these contours are the current measured contours by Planck. Okay, not very interesting. If you take the predictions from hypothetical next experiment, so this the width of these ellipses around this one are the precisions of the fast Fourier of the Fourier telescope in NS. So you may probably nicely distinguish between these two regimes. Okay, so before I finish, so the question is how to go here. That's actually pretty interesting, and it actually tells us that the story actually is not fully finished. And actually, it turns out to the last year's paper by Minksik here, and soon paper by our group, which it turns out that in this model, so you always basically produce lots of particles in the initial nonlinear behavior. You never actually get rid of scalaron completely. And in any case, you get into the situation where you have a very heavy particle, which scalaron is always pretty heavy, which decays pretty slowly. So you actually always get some additional entropy release after inflation. So you have reheating and then decay of the inflaton with some reheating afterwards. So it's actually still further problem. So still the story still is not ended. However, as far as I understand, so the preliminary estimates show that okay, these points are not going to move anymore. What is happening in this regime? There should be some small line. So basically, to nearly finish my talk, but not yet. Do I have a couple of more minutes?
Actually, 5 minutes.
Oh, perfect. So that would be enough. So, so basically, this is very interesting calculation to finish because this is the way to distinguish between the model and doable calculations. So the analysis is going on. I want to make one note about how difficult it is to predict things in inflation and print. And here the story appears that we already discussed a bit the variable choice. We basically could have used Jordan frame, Einstein frame, and luckily, as far as just change of variables, nothing changed whatsoever. Very good. However, one can go further. One can choose different formulation or different variables as a fundamental variable. One can, instead of metric formulation of gravity, one can use metric and connection as independent variables, which will lead to Palatini description of the gravity. And if coupling is minimal, then this is all the same, nothing can. However, basically the equations of motion for gamma mu nu give you the standard relation for connection, standard metric connection. However, the moment psi is non-zero, the story becomes much more complicated. Not much more complicated. The story becomes different. It's actually simpler. It's different. And the prediction for the psi and r changes. So basically, if tensor to scalar ratio in metric is 10 to the minus 3, in Palatini, it is basically never to be observed 10 to the minus 14. So interestingly, to be sure what we're speaking about, we actually need to know better what variables are true variables for gravity. Actually, one can also analyze preheating there, and it turns that preheating there is very interesting, analyzed by Ruby and Torbeck, because you very often in this potential, you many times arrive to the tachyonic regime of the potential, not just one time, but many times. And you reheat to a very high temperature there without having any problem. Okay, so to conclude, if you want to get exact prediction for the theory should be very carefully defined, and that's a universal take-home message for anybody who works with inflationary theory. If you want to play with Higgs inflation, this currently means that basically the simplest and best way is to work with combining, so making friends with the original R-squared inflationary theory. And seems that unless the scalaron is very light, unless you are really deeply, really R-squared like, it still reheats very fast and without any problem. Okay, as I said, analysis of this reheating is basically the best way to give observables, to predict observables that can allow distinguishing between these models. Thank you.
Thank you very much. Please, questions. Sebastian. Sebastian Sell.
Yeah. Yeah, thanks a lot for the talk. So I'm wondering, so in the R-squared Higgs model, I suppose your predictions somehow depend on the value of lambda, so the Higgs 4-point coupling. Is that correct?
Yes.
So which value do you take, and or can you compute the value of lambda at high energy? So if you assume that the model is only Higgs plus R-squared, can you then compute the high energy value of lambda?
Okay, that's a very good question. And my answer, yes, is a bit, it's yes and no at the same time. So what is the reason? Okay, sorry, I moved my mouse out. So as I said, basically in both models, so lambda and psi always enter in this combination, psi squared divided by lambda. So to the first extent, and basically there are, for the whole story, the relevant parameters are beta and psi squared divided by lambda. So just looking at this, you would say that any value of lambda would go, any value, the moment you're allowed to choose the corresponding psi. This is the answer no to your question. No, I can't. If you want to say yes, so the yes happens in the following story. That do I have a potential somewhere? Okay, yes, I have the potential somewhere. So let's look at this potential. So if you look at this potential, one should think that lambda is actually some function depending on some scale on mu, right? It's a running value because of radiative correction. Psi is also, strictly speaking, running, but that's mostly right. However, what happens? Mostly this scale doesn't change too much during inflation. So if lambda is sizable during inflation, then the fact that lambda changes during the running is kind of irrelevant. So basically, if change of the lambda during inflation is smaller than lambda during inflation, then you cannot say anything. However, we are living in interesting times when the Higgs mass actually predicts that the lambda goes to zero, even negative masses during inflation. And if you go to this situation, So then basically you cannot neglect. And then basically you mean that you can get features in the potential. You can get, instead of making a shallow potential, you can get, okay, I guess I have a plot for the pure Higgs inflation, unfortunately, only. Yeah, you get, instead of a nice potential that is nicely shallow, you can get a potential that has a shelf here and get interesting different predictions. In R squared of Higgs, you also can do it. And this was, so if you want to look at it, you can go to the works, very interesting works by Park, Cheng Park company, where it turned out that in R squared plus Higgs on this, so what you can do on this shell. So first you can reach larger R in this shell, which is interesting. And in R squared Higgs, you can arrange it so that you provide probe primordial black holes with enough abundance to explain dark matter. You cannot do it in Higgs inflation, but in Higgs inflation plus R squared, because you have two parameters, you can arrange good inflation and good, you can basically put this plateau to produce proper black holes. Yes, after that, if this is a situation that realizes, then the prediction would be for the basically Higgs mass where it is with crazy precision. However, not that I can really predict it. Basically, I can say that there is an interesting corner where this situation is, where all this analysis should be modified.
And just a quick follow-up. I mean, in the metric Higgs inflation, usually using the RG running as computed in the standard model at inflationary scales is not good. It's above the cutoff. Am I correct that in the Higgs-R squared it's below the cutoff? So there you can really trust the running.
In principle, yes. However, okay. In principle, yes.
Okay.
In principle, yes.
But
oh, okay. In principle, yes. But okay. So here one should be a bit careful because there you enter with a model with several scales, and then okay, whether you are very carefully computing running is a bit hard to say. For example, you can have even funny things there, like putting the scalar on below the scale where. Below the metastability scale, you can cure the metastability. This was a nice work by Dima and Anya, for example, by Gorbanov and Tokar. So, in principle, yes, in principle, it's safe. There is one more safe situation. Actually, this situation is kind of safe even in Higgs inflation, because the moment you go to this situation, your problematic scale, your psi basically goes to nearly 1, and all your scales basically go to Planck. However, okay, unfortunately, all the scales gather too close to be very, very sure that there is no problem. For example, so these ranges of prediction corresponds to some different assumptions about running. So, yes.
Okay. So you are finished?
Yes. Yes.
Okay.
Okay.
Pass to Alexei Stravinsky.
Okay. Thank you, Fedor, for this very interesting talk. I have one comment and one very general question. So, remark is one should distinguish when you say pure R squared, you have to distinguish R squared model with what main channel of decay. And as I mentioned in my talk, indeed, when you showed this 54 for a pure R squared, it was in fact it was additionally assumed when the main channel of decay is to effective non-minimally coupled scalar fields. But in case of a mixed model, in fact, the decay goes to non-minimally coupled scalar fields. And so, in fact, what I mentioned at the end of my talk, I think that the sufficiently, well, not exact, but sufficiently good approximation for this wide region. Yes, just for this one, it will be simply given by the results for R² model, but with the decay rate multiplied just 1 plus 6 high squared, and so my proposal to check if this works. Actually, it follows from the not exactly, but it's a good approximation to the numerical results obtained in the last paper by Minxi He. Okay, and my very general question, simply I want to know what you think, because all this Higgs inflation or mixed squared Higgs inflation, we essentially assume that Higgs is not simply Higgs. It is strongly not minimally coupled to gravity. So we introduced new large constant. What do you think? Is it possible to check this hypothesis by any other way apart from inflation and reheating?
Okay, so thank you for your comment. So first, thank you for your comment. And it's basically the result of Minxi so the story is slightly more complicated, but it boils out to this state. So basically, it's either this line or perturbative decay, basically, until they basically join. So that's exactly the result. And for the question, I myself don't know any other good ways except for this. So the reason is that the values of anything, of psi or beta or whatever, is beyond any reasonable collider experiment. So basically, it's pretty hard. So basically, you need gut scale collision, gut scale dynamics to study somehow, right? So very heavy dynamics you need.
Okay.
One can hypothesize that, for example, there is some tachyons, and then there are something. Okay, again, it will not go away. So one can hypothesize that something violent or non-trivial happens during tachyonic regimes in preheating. However, say, for example, gravity waves are not produced there in large amounts. So not the wrong scales turn out. So I'm not aware of any good ways. Oh, okay, leaving aside some mysterious, some tuned interest, so very interesting and tuned situations with the critical Higgs that I mentioned, but that kind of goes beyond distinguishing the theory, that kind of new regime. So unfortunately, no.
Okay.
Okay, so Massimiliano Rinaldi, go ahead.
Hi, thanks for the talk. I have a curiosity about this model. In theory, from a particle point of view, the Higgs field is accompanied by gauge fields, SU2 and so on, or depending on the representation. Do they play any role during inflation? Is that ascertained?
Yes, the gauge fields are basically, the reheating is strongly, so when you study reheating, so during inflation, no.
Okay.
During inflation, no. During inflation, no, because basically, if you calculate their masses, so the inflationary Hubble is m Planck divided by psi, and the masses of the all fields are of the order of m Planck divided by square root of psi, much larger than Hubble. So basically, that's why during inflation they're happily irrelevant. During reheating, they're very relevant. Actually, all these calculations, if you look at them carefully, I'm speaking about not Higgs field itself, but about longitudinal modes of the gauge bosons. Or about about Higgs, but about other directions of Higgs. So you can actually see, so there is very nice picture of the, so there are two Higgses. So actually the calculations numerical is with probe Higgs doublet. So that you can see, so that you start oscillating in Higgs in one direction, then it reheats and goes basically symmetry restore. So they play significant, basically major role.
Thanks.
And now, Sergey, please.
My question is about Platini gravity. Can you show?
Yep.
No. Please, yes. What I see that in the case of Platini gravity, tether to square ratio is dependent on lambda only.
Yes.
Yes. So now you can, if Platini gravity is realized, you can find some restriction on lambda, right? It is distinguished on metric cases.
We just need to measure R slightly better. Slightly means 10 orders of magnitude than our current measurement. Then yes. So in principle, what you are saying is correct. For the practical point of view at the moment, no.
Yeah, no.
Because you see the value is here is 10 to the minus 14 if you forget lambda. And the current bound is what is now 0.05 or what? Something like this.
Okay, it is a result only for Higgs inflation without a square term, right?
Yes.
Okay.
And now, Wickman, please.
Hi, Fed. Thanks a lot. It's very nice talk. I'm just slightly confused regarding this kind of very sharp production of longitudinal bosons. It's a very nice picture, but usually kind of very, very naively, this one. One could say that if you have some oscillations which are kind of faster than Planck, then on effective field theory grounds, you should just forget about them, just throw them away by smearing, right? By averaging. And then don't be worried, right? In
So
some
kind of,
sense.
Sasha, kind of this is what's happening the moment you regularize the field.
Yes.
Kind of this has happened. This was found by Alexei and company.
Right.
So by Minx, so Minxi, Park and Alexei. So that this peak smears so wide that it becomes fully irrelevant. That's kind of yeah. So the only thing that I can say is that you are fully right.
Okay.
Okay. So thanks to everybody for an interesting discussion. Thank you very much.